And you see, the idea was that philosophers believe that it's an indivisible object whose shape dependent upon the microphysical properties like water. The atoms would be slippery. That's why you see the water is slippery. That's the understanding. And for iron, the atoms will be very solid. So this was a worry. So people wanted to know. It wasn't until 1902 when John Darting based his experiment on research, proposed that elements were made up of specific atoms and that would combine with each other and were indivisible and could not be altered by chemical means. Those are early ideas about the atom. Now, then the models evolved very rapidly, starting with the Thomson's discovery. So that's why we're talking about the Thomson's model first. So see what he did here. From this experiment, he came out with the Plum pudding model. If you look at this, it's like a satin cake that is having some stuff inside. So the pudding, we have currant and this pudding. So the name came from a kind of cake that was, in the English culture, they have that kind of cake. So we see Thomson's discovery of the electron was the first evidence that the atom is not the underlying structure of the matter. We said that matter is made up of tiny, indivisible particles called atoms. So, and that is the ultimate end of matter. It means I cannot go beyond that. It cannot be divided further. That was the idea. But the J.J. Thomson's model, the Plum pudding model, gave us an idea of, he proposed, that is around 1904, he proposed that the electrons move about within the mass of a positive sphere. He never really said what these positive charges were, but it looks like the plum pudding in English. So now, but the model could not explain the different wavelengths of the light emitted by excited electrons. That was a problem for him. Now, you see, like what I said, this was his model, that the electron, the atom now has a positive charge sphere, and embedded in it, you have the electrons that are embedded inside. That was a picture given by JJ, that is Joseph John Thomson, and he was able to actually give us a small window as of what we are trying to discover. We're still trying to discover what is this atom, what is the constituent of the matter. Now, if we know what is inside the matter, we'll be able to know or describe matter properly. So now, to his greatest surprise, in those days, they have individual experimental discoveries. So another gentleman called Rutherford decided to use some of his guys, Marsden and Geiger. The two of them were instructed by him. He didn't do the experiment actually, but he instructed his guys to go to his lab and use some sources of radioactive material and try to bombard the gold foil there and see what will happen, because he was trying to debunk this. If this guy says this is the picture of the atom, then if the picture of the atom is this, then we needed to know whether this picture is true. So he gave this assignment to his friends, and they were able to do this scattering experiment. This is the famous scattering experiment by Rutherford. You can see that the radioactive sample was penetrated, and they have that screen at the back that detected the alpha particles that were some passed undeviated and some were deflected at some angle. Some of them even deflected at higher angles such that they appear to be coming back to the alpha particle, meaning they bounce back directly. So that's a breakthrough. So okay, you said that the atom is made up of this, meaning it has a positive charge sphere and the electrons are stuck inside like that. We needed to verify whether that's true. So they bombarded the gold foil by its own indication if the content of the gold must be somewhere like this. These are all gold atoms. So if I put something here, just draw. Now let's see, there was a positive material here, positive material here, there, and here, and here. So those positive materials, we didn't know the name. I'm calling them positive because he's coming to discover something. That is the nucleus. He's trying to discover something. So now, as the alpha particle, some of them pass undeviated, and some of them that went very close suffered some deflection, as if they had a head-on collision. But there was an idea of force between two particles. either in terms of mechanics or in terms of electrostatics. If I go closer, then there's going to be a very large force, because if you go closer, you have a small distance. So the smaller the distance there, smaller the distance, the bigger the force. So what will happen is it will be deflected backward. And now when that happens, then that equation leads to that relationship between them. So we know that the closer you move towards that, the bigger the force. And that force was equivalent enough to bouncing back that particle. Yes, and those ones that we are far away from that is the same. If I have a smaller force, I have a bigger distance. If I have a bigger distance, then there's going to be a smaller force. Then that force will obviously not allow the alpha particle to deflect much. So those ones that we are lucky to go closer to the nucleus, that's no idea about nucleus, it was just a positive material. They were almost suffering from a head-on collision, such that they were repelled back. And that was a surprise to the two guys that were watching this in the lab. And they concluded that after this, you now have the picture of the atom. If that picture is related, now if actually they look at the discovery, after that experiment, this was what was discovered. That the Plum pudding model of the atom, positive and negative charges are dispersed, like what I told you, and evenly throughout the atom. That was the Plum pudding model by J.J. Thomson. And this model, we are correct. So if this model was correct, then we were going to see the high energy alpha particle would be slightly deflected by weak electric fields as they pass through it. So this was the picture. If this guy's model was correct, you are going to see a small deflection, because remember, the alpha particle is a very heavy particle and it's coming to interact with a very light material, which was the electron presumed to be. Now there was going to be a little deflection from it, but we didn't see that one. So now what they saw was a picture like this. This picture was what they saw. They saw that some of the alpha particles were deflected at some angles, based upon that equation that I just proved here. So now, this led to the discovery of the middle part of that atom. You see, we are going gradually as we are entering into the discovery. Now we see that the alpha particle that had a seemingly head-on collision with this material in the middle, which was not known, it is possible that those alpha particles that bounce back must have got a head-on collision with a particular heavy material that is in the center of that atom. That was an interpretation of what they saw. And in that evening, you can see from Rutherford's own idea. This was what I was trying to explain there in my diagram. You see the account that the angles were deflected based upon this equation. Now the equation is what I just stated. So after that discovery, this is a statement in his own handwriting. Then I remember 2 or 3 days later, Giga coming to me in great excitement and saying, we have been able to get some of the alpha particles coming backward. So it was quite the most incredible event that ever happened to me in my life. That's a big statement there. Now, it was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it came back and hit you. So that was going to be something we will not believe. Like you send the shell and the shell on a tissue paper, the $5 tissue paper, and you see that shell penetrated onto that tissue paper, and that tissue paper repelled that shell back. That would have been something we cannot even imagine there. But that was the imagination, and this is what they saw. As they saw the alpha particle got that head-on collision and came backward there. So now you see, this was what they were expecting. So that the alpha particle, most of them must have gone through. That's what was expected. That the Plum pudding model only lasted for 5 years. So remember, when we go back to the question, you will see some of these questions coming. When work was done by one of the Thomson students, the Ernest Rutherford and the Giga, as I just stated them, named them. So Marsden established that the positive charge was concentrated in the tiny nucleus of a diameter 10 to the power minus 15. See how small that is. So now see how that tiny space there is where the heaviest part, the whole mass of that atom we're talking about is concentrated in the center. You can see. Now they aim a beam of alpha particle at gold foil, and if the atom were a plum pudding, they expected that the alpha particles would just plow through as shown in the top right corner, as I explained to you. But to their surprise, they saw a different thing. So now, Rutherford's model, they were forced to come out with their own model, trying to contradict and with experimental proof that this model could not be a proper model, this model could not be a correct one. So look at the relationship there. Whether it is in terms of mechanics, like I said, you have this is this and two objects moving in that order. Newton says so. It's a when two particles or two objects are separated by a distance r. So the force between them is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. That's a concept that they knew. So as this alpha particle that was going towards that giant central core, there was going to be an attraction, there was going to be a distance between them smaller. So those alpha particles that went smaller, closer to it, they were able to have a bigger force that repel them backward like that. So that is a relationship that they all confirm. So now let's see what happened. Now the Rutherford model suggested that the atom is a vast empty space, of course. Now let's see what this model brings up. So the questions follows. Remember the story? It was JJ that discovered the plum pudding, and now Rutherford was able to debunk that and bring some other model that we want to actually investigate. So the first question under Rutherford's model, we said the good fuel experiment performed under Ernest Rutherford's direction confirm what? You know, you can see first it says confirm the plum pudding model. That was confirmed that it was J.J. Thomson's model. Plum pudding was for J.J., not for Rutherford. It led to the discovery of the atomic nucleus. In fact, that central core was what resulted to be the nucleus. That was one discovery. From this experiment, we are able to discover the atomic nucleus. So B must be the correct answer from that. And it was on the basis of Thomson's model. That was wrong. So you have A, C, and D, all of them wrong. So we have B as the correct one. It led to the discovery of the atomic nucleus. So that is how we were able to consider the atom of having a central core, which is that nucleus. Mass of the atom is concentrated. So we have that atomic structure. Let's go to question number 2. In the Rutherford's nuclear atomic model, the heaviest part of the atom is A. It says very small and surrounded by electrons. It said its positive charge in the atom is uniformly spread. That's wrong. We have the nucleus is physically the largest compared to the rest of the. I just told you, I emphasized the structure. I just emphasized that to you, that it was a tiny space somewhere there. So that's debunked. That's C. Now they say the positive charge surrounds the electrons which are in the center. That's wrong too. So B, the positive charge in the atom is uniformly spread. Is wrong. B, C is wrong. D is wrong. So the correct answer is the very small. It tells a very small and is surrounded by the electrons. So that model, the nucleus, was the very small one which was situated at the center there, and it was surrounded by the electrons. That was Rutherford's model. So in this question, it is A that is correct. So we move. Now the gold foil experiment performed in Rutherford's lab confirm what? Now remember what I've just said, that after the experiment, there was confirmation. It will confirm, let's go through them. One, it confirms the plum pudding model. No, it did not confirm that. It led to the discovery of the atomic nucleus, of course. That's how we were able to look at, to know that the center of the atom is having the nucleus, which is that atomic nucleus we're talking about over there. This is the central core. How did we know? If there was no experiment, we are just going to hope on the J.J. Thomson. There was no need to know whether the central core contains that heavy part, which is the nucleus. So it was based upon the Rutherford experiment that we were able to conclude that the central core contains what is called the nucleus. Now, it was on the basis of Thomson's model. That's wrong. So it led to the discovery of the atom. That's the correct one. Let me read the questions. I'll go through the options again. The gold foil experiment performed in Rutherford's lab. A, confirms the Plum pudding model of the atom. B, led to the discovery of the atomic nucleus. C, was the basis of Thomson's model of the atom. And D, it utilized the deflection of beta particles by gold foil. That is wrong. So B, it led to the discovery of the atomic nucleus. B is the correct answer there. So we proceed to the next question. Now look at it again from what I've said. I said in the Rutherford nuclear atomic model, look at the first one. Say A, the heavy subatomic particle reside in the nucleus. Now the principal subatomic particle all have essentially the same mass. That's not correct. Now the light subatomic particle resides in the nucleus, and this D says the mass is spread essentially uniformly through the atom. That's also wrong. Now we look at the heavy subatomic particle resides in the nucleus. So now this heaviest part of it is inside that nucleus. We said that before. So that is A in that case. Now we look at the next question. It says the Plum pudding model of the atom was important because the Plum pudding model was very important. You know, there is foundation for everything. You could just come and just say something. You must have started somewhere. So we still give him kudos, matter of fact. So here, A, it says it was correct in every manner and lasted for many years. Remember when I was giving my lecture, I just told you that this lasted for only 5 years. It lasted for only 5 years, so it did not last for many years, as the question says. That's wrong. Now B, it confirms that electrons are a negative charge. It didn't confirm that. It didn't confirm that at all. Now C, it includes protons. Never confirmed that. Now it was the first model that illustrated the underlying structure of the atom. That's very correct, because that is what it was meant to do. It was actually the first experiment that actually give us the underlying structure of the atom. And never mind if we compare the models of JJ as to the models we know presently, you must see that that is crude. That's why we even call it a crude model, because you can see that it is not in conformity with what we know now. But he did some great job there, so we give him kudos. So this pudding model of the atom was important because the D there is the correct one. It was the first model that illustrated the underlying structure of the atom. That was the model that gave us the foundation, what we know today about the atom. So we give him kudos. So that is D correct there. Now we have the next one. The Goldfield experiments performed under Ernest Rutherford's direction. Like I told you, it was under his direction when his two guys, Giga and Mars, then were able to perform the experiment. You see, A, it confirms the Plum pudding model of the atom. Of course, I'm repeating the same question over and over just to let you understand. The Goldfield, the B says, led to the discovery of the atomic nucleus. Of course, I've said that before, so this question repeats. So I just move again. Now, the heaviest part of the atom is this question have been answered. Yeah, I've answered that question. Now, we look at another model, another contributor. The first, remember the sequence of how events are coming here. The first was based upon the fact that the atom we have got a foundation about the atom right now. We are able to see. So see the crude model. From the crude model by JJ, we are able to look at the Rutherford model. The Rutherford model. So another contributor needed to tell us something. So the problem that Rutherford encountered here was massive because he just gave us a central core. That is true. You have protons, neutrons in there. That was the nucleus, according to him. He said the electrons cloud around the nucleus, yes, in the extremities, yes. But this model round the Rutherford model ran into problem when we wanted to look at the force that holds objects in their orbit. That force is the centripetal force. And it is under classical mechanics that says that if an object goes around a circle, it radiates energy. And if it radiates energy, then it is possible that as it is losing energy, those electrons will spiral, and they lose energy so much that they will be able to spiral inside the nucleus. So that third part of the atom will not exist. So Rutherford's model will go into a problem here. Yes, the electrons are orbiting around. But if we consider the concept of classical mechanics that tells us that when there is an object going around, it will always radiate energy. And if you radiate energy so much that you lose a lot of energy, you will not be able to complete the orbit, and you'll be spiraling inside the nucleus. And when that happens, we'll talk about atom collapse. So that third part of the atom will not exist. So the electron part of the atom will not exist. So that was another problem for this model, which is Rutherford's model. So we needed to correct that. Now, how do we correct that? It's one gentleman was part of this and decided to move away from classical physics and go to quantum physics. What is that quantum physics actually? It's actually the physics that explain the basics of or the physical properties of something based upon its quantum number. And your quantum number, it's actually a number that allows a physical quantity to exist. So if we needed to study this to make sure that the third part of the atom is not broken, then we needed to allow the electron to be on the orbit. But our concept in classical mechanics will debunk that. Will tell us that as the electron goes around, it will lose energy. And if you lose energy, then it's going to spiral inside that nucleus. And when that happens, then we'll have a problem there. So there's an atom collapse. So that model will have a problem. So we needed to shift from classical mechanics to quantum mechanics. So quantum mechanics and classical. Classical physics is basically Newtonian physics. That is, we are Newton's laws most of the time. So we needed to move away, and we know that electrons can exist as a particle, and at the same time they can exist as a wave. So we needed to look at the particle under this classical model. We do not conform to the laws of Newton. Because of that, considering the electron as a particle, and it will radiate energy, so the electron will not exist there, it will not stay there. So when that happens, then we are going to lose that part of the atom, and that's the problem. So somebody needed to rescue them. That's Mr. Bohr. Mr. Bohr now said, what if we consider the electron as not a particle? Because electrons can be both particle and wave. So he needed to rescue, and he said, let's consider the electron as a wave. And we know that electrons, considering it as a wave, we know that every matter has matter wave around it. So if we consider the electron as a wave, then there's a concept that says that if the particle which is considered as a wave has a wavelength, if the part where that particle is running is equal to its own wavelength, then that particle will not release energy. The energy will be quantized. So we needed to use that concept, that if the electron is not considered as a wave, and its wavelength is equivalent to the circumference of that orbit, the moment its wavelength is equivalent to the circumference of that orbit, then that electron stroke particle will not release energy. And because it's not going to release energy, they could stay in a quantized or discrete energy state. It will be on that level. So because we needed it to stay here, so we need to bring that concept inside. So Niels Bohr brought in the concept that if we consider the electron as a wave, then the wave has a wavelength, then we can assume that if the wavelength of that wave, now the electron considered as a wave, is equal to the circumference of that orbit where that wave is going around, then the wave will not release energy. And when that happens, then there's going to be stability. So the electron will stay on that orbit. So that is the more reason why he now suggested that let's consider the electron as that. So that helped to maintain the third part of the electron, meaning the collapse that was supposed to be considered under classical mechanics that will allow that electron to lose energy such that it will sphere inside the nucleus. Now we have got a solution to that. We will now consider the electron as a wave, and if it's a wave, then we can also look at its wavelength. And if its wavelength is equal to the circumference of that orbit, then that electron will not release energy. So it will be in the quantized or discrete energy state. So that level is what is called a quantized energy state. It will not release energy. So now that was a breakthrough. So Niels Bohr brought that. So we say the hydrogen emits many wavelengths of light when it is excited. And this is what Bohr explained when the model was introduced in 1930. That's recent. So now you have the spectral lines. If the electron is moving, now we look at the model. I've already brought the contribution made by Bohr. Bohr was able to give us this model that it is able to keep the electron on that orbit based upon the fact that it is now considered as a wave. So now, with that breakthrough, we can now talk about another contributor. Now, the question came, okay, if we now consider the electron as a wave up there, some of the things I'm saying now, you can't see them on the screen there, but I'll just summarize here. You can see this electron now considered as a wave. Then what is going to be the motion of that electron now considered as a wave? Now, Niels Bohr suggested that the motion of that electron is going to be in one dimension. And if it's going to be in one dimension, then we are going to have another problem on that model. Niels Bohr's model actually suggested that the electron can now occupy certain allowable energy levels, not all levels, discrete energy levels. And in that level, they are able to transit, meaning they can move from higher to lower, lower to higher like that. But the problem, the model ran into a problem because we needed to explain how will the motion of the electron be, how will the electron move on that orbit. And to Niels Bohr's idea, the electron will move in one dimension. So if the electron moves in one dimension, so they have to ask him, if it is moving in one dimension, then let's forget about the atom now, and let's look at the bigger picture. Of course, the atom is just a miniature of the solar system. So if you look at the solar system, if the sun is the center, and the planets are somewhere there, let's say the planet Earth is somewhere there, if you see the electron is going to move in one dimension, then it is going to violate the motion of the planet as they go around the sun. Because the motion of the planet do not conform with that idea. The planet, like for instance, the Earth, even as it's orbiting right there, it is still spinning around its axis, along its axis. So it can be a perfect explanation about the dimension, the one-dimensional motion of the electron. So we needed to move away from that. So he had a problem. So people needed to rescue him. So the model that came into the rescue was a quantum model. Now the quantum model has shifted from the classical explanation of things. Now we are now under the quantum principles. So we are considering the electron as being a wave. If you consider the electron as a wave, then we are now thinking about it in the quantum model. So now in this model, we needed to describe the movement of that electron based upon quantum number. But there's a part of physics that talks about quantum physics, which talks about how the physical properties of something is described based upon its quantum number. And those numbers are numbers that allow a particular physical quality to exist. So now, if we can shift to that, we needed to now describe the motion of the electron based upon its quantum number. So that's why the quantum model came in there. So the quantum number is the one that actually allows a physical quantity. So that if we discuss its motion based upon the quantum number, then we were able to now combine together and try to describe the motion in violation to what he was saying. Here, he said the motion of the electron is going to be in one dimension. So we needed to correct that error. So Niels Bohr's model ran into that problem. So they needed to correct it. He accepted that if it was one motion, then the atom being the miniature picture of the solar system, the Earth would have just been in one-dimensional motion. We are going to have a rotational along its axis. It's not going to be rotating along. So we needed to describe the model based upon its quantum number. So the first quantum number that ran into your mind is that It's that of the first quantum number, which was the principal quantum number. So that principal quantum number, it tells you how far is that electron from that central core, which is the nucleus. It means it is describing the radius of that electron, where it is. So it describes the radius of the electron, and it's also describing the energy content of that electron. So that first quantum number was called the principal quantum number. And that was used to establish the energy and also know the radius of that atom. So that equation, if you did the electrostatic forces from my previous work there, we will come to a point where the principal quantum number will now be the quantum number that is used to estimate or to calculate the energy of the electron at that level. So now let's say it is given by this, also 8 epsilon squared. It's a big equation, but don't worry about these constants. Now here, I said the first, which is the principal quantum number, needed to actually tell us how far is the electron from that orbit, meaning it's telling you the radius of that orbit, and also it tells you something about the energy of that level. And how we want to calculate the energy of that level, we'll talk about the mass of that, the electronic charge, and we have the Planck constant. Remember, as the electron is coming to transit, it's going to transit in the form giving out energy or absorbing energy. It can transit. That's what Niels Bohr concluded. Yeah, you see, the electron can actually occupy fixed energy level, but it has the ability to also transit from upper level to lower level to upper level, as the case may be. So as it is transiting, it needed to actually give energy or absorb energy. If I'm transiting from a higher level to a lower level, I need to release energy, emit energy. And as I'm emitting energy, that energy comes in the form of light. And that light is related to its frequency. The light that was emitted as the electron transits from that point to that point, or from this point, is going to be absorbing energy as it's moving. That's Niels Bohr's conclusion. That yes, the electrons can occupy fixed quantized energy level, but as they're there too, it's not all orbit they are going to occupy, but they will have a fixed energy at that level, because at that point they are considered as wave and they will not release or radiate any energy. So they have a fixed amount of energy there. But they have one opportunity. They can move from upper level to lower level. They can emit energy, come back. It's like a guy moving from grade 12, come down to grade 10. Or another guy that is so smart enough that can swallow all the syllables from grade 10, 11, and just switch to grade 12. So you can transit. That transition needs absorbing energy or releasing energy. As you release energy, you are releasing it in the form of light. That's what the electrons are doing. So when they release it in the form of light, now the frequency of that light has to do something with the energy of that transition. So that energy is directly proportional to the frequency. That was established by Planck. Max Planck brought that relationship. And because of that, we now know that Max Planck, that's the Planck's constant, that's the one over here. So you now know the epsilon, that is the permittivity of free space. That's the whole constant also. It's 8.3 times 10 raised to the power minus 12. So all of these are constants. We have the mass of the electrons, 10 raised to the power minus 31. So that's one here. We have the electronic charge. I just gave you that, 6 times 10 raised to the power minus 19. Yep. And I've got the epsilon. This is the epsilon. Now we have Planck's constant. It's 6.6 times 10 raised to the power minus 34 GS. And all of these are constants. So the only guy that is going to be the variable there is n, which n tells you the radius. So if you go to this, you move to one level. This is the first energy level, second energy level, in that order. So the n keeps changing as I'm moving. If you consider hydrogen, it gives you its own energy level at its lowest stage. There you have for hydrogen, it's 13.6 electron volts all over n squared. So you can see that all of these are all constants. So for hydrogen, you have this energy equation for it. So now this equation is actually used to describe the first principal quantum number. That is what is giving you the energy of that level and also the radius. That's what I told you. So another problem was, what about the second quantum number? I've already said this is the first quantum number, this is the principal quantum number. The second one was the angular momentum quantum number. Angular momentum quantum number. What is that angular momentum quantum number? For as much as the electron is going to orbit around that that is going around the orbit, it needs some angular momentum. You know, the velocity is going to be, it has a particular velocity as it's going around, and that velocity multiplied with the mass will give you the momentum. So the magnitude of the angular momentum is what is called the second quantum number, which is there for objective purposes. They can ask you what is the second quantum number representing. It represents the angular momentum quantum number. So if I subject this atom into a magnetic field, the magnetic field will also affect the motion of that electron. That effect of the magnetic field is what is called the magnetic quantum number. So the effect of the magnetic field on the motion of the electron is what's called the third quantum number. It's called the magnetic quantum number. And now the fourth one is, we have already said that it is a miniature of the solar system. So meaning what happens to the solar system is also happening. As this Earth is revolving around the Earth, around the Sun, it is also spinning around this axis. So now as the electrons move in that orbit, they are now also spinning along. As they are spinning, the effect of the spin of the electron will give you the fourth quantum number, which is the spin quantum number. So this fourth quantum number describes the motion of the electron on that orbit. So it tells you now that if I want to actually keep that orbit, I need to classify the orbit based upon the motion of the electron based upon its quantum number. That physics that describes allowable values, allowable the physical property of something to be studied based upon its quantum number is what is called the quantum physics. A very interesting part. You can see that, you can do more of that later on. But now for your syllabus, we just want to stop here and now bring out this model. So the other question that came was what will happen to the electrons? As what I've said here is what I've just summarized over there, what the planetary orbits of this 19th century, as I said. Now you see what I was saying there, all the forces I discovered there, or what I said there is what is in that equation, and Bohr's solution. So let's see what was the solution of Bohr. So now see, now this electron, like I told you, it can move from one energy level to another. It can move, like you see the green arrow there. That electron is transiting from level 2 and going to level 1. So it has to emit energy. It has to emit energy, and according to Planck, that emitted energy is going to come in the form of light, and that light has frequency. That's what is the frequency there I was talking about over there. So now you see that equation. The photons that is giving out is the energy, is the packet of energy that that's going to be sent out. That packet of energy has a relationship with the frequency of the light, because light is a bundle of the packet of electromagnetic radiation is what is called photons. You know that already. So now this equation is what I just stated here. So see what will happen. If the electron is now moving from one orbit to another, and lower orbit to higher level to lower, we will talk about the transition. So the first thing is, what is that transition? The transition is, first, yeah, as it is transiting, we are supposed to have transition first of all. As it is transiting, I'll just define that for you. If the electron is moving from upper to lower, lower to upper, it is transiting, meaning from the word trans. As it is transiting, it can absorb energy and go to higher level, and it can release energy and emit energy and come back to lower level. So now if that is going to happen, what if that light that is giving out during the transition, if the light is incident on the screen, you will see that that light gives the characteristic spectrum of the atom. What is happening inside the atom? It's a picture. So that those lines are giving up in the form of spectral lines. So we can see the next slide that will come. It's a Bohr reason. Yes, that was what I was talking about, transition. Now, the process by which the electron transits move from one energy level to another. And as it is doing that, it can absorb energy during this transition and move. And that energy is given in the form of light, like I said. And you can see when this light is incident on the screen, it will give the characteristic spectrum of the forms of light that are there. The energy that is the transition that is given, will give it in the form of the lines there. So if you follow up the slide, you can see there are two types of spectral lines. You know, we have emission spectrum and you have the absorption spectrum. Meaning, if I'm moving from higher level to lower level, I'm emitting energy. Then I can move from lower level to higher level. I also absorb energy. So we have two forms of that transition, and both of them involve energy. So that's what I've defined it so far for you. You have continuous spectrum. Continuous spectrum is a type of emission spectrum. All of them are on that emission spectrum. What is that continuous spectrum? In this spectrum, the lines, almost all the lines are visible, and it is produced by hot bodies. The sun is producing that kind of spectrum right now, and it contains all the wavelengths in the specific region of the spectrum. You can see all the wavelengths. It travels, it gives it in that form. You will see that all the lines are visible in that particular region. This is produced by continuous spectrum. That's the spectrum produced by the continuous spectrum. That's the lines there. So the second one is the line spectrum. For a line spectrum, some of the lines are absorbed. Few lines are visible. It's few lines that are visible. And we have the band spectrum, which two or more lines will come together, clog together, and they form the band spectrum. So as you see the definitions there, the line spectrum, we can see that those ones in gases like hydrogen and so on. And the band spectrum, you can see that in even the blood. The blood gives this kind of spectrum. And we have some other materials that will contain molecules. They also give this kind of spectrum. So we have the types of spectrum. I've already given that. So what happens if the electron is now supposed to transit? You know, remember I just told you that it's transiting, meaning it's moving from one energy level to another, as the case might be. But now we want to see what will happen if this guy is moving from one energy level to another. What will happen? It is going to be absorbing. Okay, so now looking at the transition, the electrons can move from one level to another. This is yes, from my transition, the electrons can move from one energy level to another, and I can also transit from. So let's look at transition A and transition B. This is E3 and E4. If I have an electron moving from a lower level, like a hydrogen-based atom, for hydrogen-based atom, the energy it uses is going to use to absorb to one level is equal to the same energy that is going to release to come back to that same level. So now, if it is going to do that, then we'll have a transition. Let's say a transition that is based upon, let's say, transition A, and transition B. For transition A, the guy is emitting. So it's moving from a higher energy level and coming down to a lower energy level. And transition B is absorbing energy from one energy level to another. So we have already been able to explain the energy states there. So you see the levels. If I go backward, you will see that equation. Now we have the energy levels. That's the ground state. That's the lowest energy state of the spectrum. That's the lowest energy state. And you have other states that are excited. And we have the ionization state, where the electron will gain enough energy such that it can, that is at infinity, it can go at infinity. So we can go towards out of the boundaries of the atom such that we gain a lot of energy. That energy is what is called the ionization energy. So like I described that, you see, lowest energy level is what is called the ground state, and the higher energy levels above the ground state are called excited state. So I'll just round up there from that. So let's go to the next slide quickly. Now, what I was saying here is what happens when the electron transits from one energy level to another. Now, for this transition, this is a emission spectrum. The guy is moving, the electron is moving from energy level 3 to energy level 1. So it's transiting from that level to there. So now the difference between the energy levels is what is given by that equation. And if I'm transiting this time also, I'm moving from energy level 1 to energy level 3, 1 to 3, that is absorbing, that I'm absorbing, this is absorbing. So I absorb energy, I go to the higher level, I have E3 and E1. Now, there are two ways you can do this. You can also subtract from the lower to the higher, but you must be able to explain the negative that will come in. So now, but for now, we want to avoid the negative and we just use this. So now we have the absorption, as I've said so far. You see that equation over there. And you have the next one, which is emission. That is what is there. And as they are emitting, they are always giving out energy in the form of, or absorbing energy in the form of light. And when that light is incident, that light has a frequency. So that's how that equation came. So HF from Planck's constant. The energy is directly proportional to the frequency. You know that already. Now, for your exercise, now we can solve this problem. Then I'll give you some homework or something. So let's see what happens here. You have a certain atom emits ultraviolet photons of wavelengths. The wavelength is already given. This equation, the equation is lambda there. So lambda frequency can see be like that. So I can substitute that because it's light. Light is electromagnetic. So I can substitute the frequency in that equation. So I can get my equation there. This is hc over lambda because I have already decided to substitute that for that. So now if I substitute the two, we'll now have from that question, it says a certain atom emits ultraviolet photons of wavelengths. The wavelength is given somewhere there. So, and underneath the question, you have Planck's constant. Planck's constant is 6.6 times 10 raised to the power minus 34 Js multiplied by the speed of light. Remember that the transition is given up in the form of light, and that light has the speed. The speed is 300 millimeters per second. This is moving, the light is moving at a speed of 300 millimeters per second. Very fast. So now we have the wavelength, and the wavelength was given there. So it's 2.4 times 10 raised to the power minus 7. Now if you punch that on your calculator, you come across a figure like this. 10 raised to the power minus 9, minus 19 joules. So you can see that the question says now insert. So that's what is there. You say insert this, copy this question in your answer booklet, and you now see where this transition takes place. So if it is on that's our transition level, you look at the emission energy, like you see energy level 3. If you go back to the energy levels, you will see that energy level 3 is this figure, it's 8.2. So, and in this question underneath, you will see 8.2 from the third level there. So it's going to be from the third level. That is the third level. That corresponds to that energy at the third level over there. Now, if you look at the question, it says a certain atom emits. And when you are emitting, you are releasing the energy from higher level to lower level. So it could have been an arrow coming from that level 3 downwards. So it's coming from one energy level 3 and moving down here. So that is the arrow that was supposed to be put over there on that equation. So now, with what we have said so far, I want to recap. Then the next question will be your classwork. This is your classwork or your assignment. Try as much to do all of that. You must be able to define the spectral lines by now. I've defined all of that for you. And you must be able to yes. So I want to read the assignment for you. Now, the exercise or the classwork is that define atomic spectra. And number 2, differentiate between emission spectrum and absorption spectrum. That's Roman figure 2. And you have a diagram. Now that's the diagram. That's give you the energy levels, just what I've explained so far. Now, they said the diagram above illustrates an electron transition. I've just explained what is transition for you. And it is moving from energy level N3, that's the third energy level. That's the second excited energy level. That is the third, N3, to N1. And the question says, now you calculate the energy of the photon. So watch this. You're supposed to calculate the energy of the photons. Yes, so the equation is here. So you must be able to use this equation and get that because the arrow is coming down, so it's telling you it's an emission process. So watch out for the equation. It's just a guide to the solution there. If you look at it says also find the frequency of the photon. If you want to find the frequency of the photon, the equation is here. You've already got the energy. That's the energy E. Now you've calculated differences between the energy levels there from that formula. Now you'll be able to use that answer and find the frequency. And you have Planck's constant underneath under the question, so you don't have a problem with that. Now we have this next one says then calculate the wavelength. Now the wavelength is there, so you can calculate the wavelength. If you can make this wavelength the subject of the formula, you have the C and the energy. So you have a guide to that question. You must be able to use this equation, the 3 equations I gave you, to be able to give you the transition, to give you the equation that connects the energy with the frequency, then you get that. So that's all for you. So thank you very much, and that's where we can end for this lesson. Thank you for your audience.